Welcome. In this presentation, we will review hypothesis testing modeling. Today, we delve into the world of statistical analysis and explore the powerful concept of hypothesis testing. Hypothesis testing is like a detective's magnifying glass in the world of statistics, allowing us to draw meaningful conclusions about entire populations using just a small piece of the puzzle, the sample data. But why is hypothesis testing so crucial? Let's uncover its significance together. It forms the foundation for drawing conclusions about populations based on limited sample data, acting as the cornerstone of making sense of the vast and complex world of statistics. It's the bridge that connects what we observe to what we can confidently say about the entire population. Scientific rigor is the backbone of credible research. Hypothesis testing ensures that our findings stand up to scrutiny, providing a solid foundation for scientific advancement. Imagine it as a compass guiding decision-makers through the vast sea of data, helping them navigate towards informed and sound choices. Much like a risk assessment tool, hypothesis testing allows us to gauge and manage the risks associated with our conclusions, striking a delicate balance. And finally, it propels us forward on a journey of continuous improvement. Each hypothesis tested, refined, and tested again contributes to the ever-evolving landscape of research methodologies. Here are key concepts that form the bedrock of hypothesis testing. Let's unravel these concepts together. First up, we have the null hypothesis, 8-0. This is our default assumption, our starting point. It's the belief that there is no significant difference or effect in our observations, a bit like the status quo or the baseline hypothesis. It's the foundation upon which we build our investigation. Now enter the scene, the alternative hypothesis, H1 or Hay. This is the bold claim, the hypothesis that researchers aim to support with evidence. It asserts that there is a significant difference or effect lurking within our data. It's the challenge to the status quo, the call for change. Next on our list is the significance level, A. Picture this as the threshold for skepticism. It's the probability of rejecting the null hypothesis when, in fact, it is true. Commonly set at 0.05, it signifies a 5% chance of making a type Y error. It's the cautious line we draw in the sand, reminding us to tread carefully when making decisions based on our findings. So, remember these key concepts. They're the compass guiding us through the intricate landscape of hypothesis testing. Let's keep exploring. Let's begin with the formulation of hypotheses. We define the null hypothesis, 8-0, representing the default assumption, and the alternative hypothesis, 8A, that we aim to support with evidence. Moving to the next step, we select a significance level, A, often set at 0.05. This threshold guides us in determining the probability of rejecting the null hypothesis when it is true. Now we collect relevant data through experiments or observations. The quality and quantity of the data play a crucial role in ensuring the reliability of our hypothesis test. With the data collected, we move to the analysis stage, employing statistical tests based on data type and hypotheses. The goal is to assess the evidence against the null hypothesis. Finally, we make a decision based on the analysis. If the evidence is statistically significant, we may reject the null hypothesis. Otherwise, we fail to reject it. This decision-making step is critical in drawing meaningful conclusions from the hypothesis test. Let's delve into the critical concept of types of errors. There are two main types we need to be aware of in hypothesis testing. Type Y error. This occurs when we incorrectly reject a true null hypothesis, often referred to as a false positive. The implication here is that we falsely conclude that there is a significant effect when, in reality, there isn't. Type 2. Error. On the other hand, A type 2 error happens when we fail to reject a false null hypothesis, termed as a false negative. In this case, we miss a true effect, mistakenly accepting the null hypothesis. It's important to note that there's a trade-off between these errors. Adjusting the significance level, A, impacts the rates of type 1 and type 2 errors. Minimizing one increases the other. Understanding and minimizing errors is crucial, especially in fields like healthcare, where incorrect decisions can have serious consequences. Moreover, the concept of statistical power is vital. It represents the ability to detect true effects, 1, type 2 error, and is a key consideration in experimental design. Ensuring a balance between these types of errors is fundamental for sound decision-making in hypothesis testing. Let's walk through an example of a fuel efficiency enhancement study using the MT-CARS dataset. In the first step, we formulate hypotheses. Null hypothesis, H0. The fuel efficiency enhancement treatment has no significant effect. Alternative hypothesis, H1. The fuel efficiency enhancement treatment improves fuel efficiency significantly. Moving on to the second step, we choose a significance level, A. It's a critical decision in hypothesis testing, often set at 0.05, 0.01, or 0.01. This significance level determines the threshold for considering evidence against the null hypothesis. So, in our example, we might set alpha A to 0.05, indicating a 5% chance of rejecting the null hypothesis when it's true. This is a common practice in hypothesis testing and helps us control the balance between type 1 and type 2 errors in our study. Let's continue our example of the fuel efficiency enhancement study using the MT-CARS dataset. In this phase, we're on to step 3, collecting data. We'll simulate data using the MT-CARS dataset. We're introducing a treatment variable based on a condition. If the miles per gallon, MPG, is greater than 20, the treatment is labeled as enhanced. Otherwise, it's labeled as standard. This simulated data set will be the foundation for our analysis in subsequent steps of the study. Continuing our fuel efficiency enhancement study example with the MT-CARS dataset, we now move to step 4, analyzing data. To visually assess the distribution of outcomes, we'll create a plot. This bar plot displays the distribution of outcomes based on the enhanced and standard treatments. Visualization is a crucial step in understanding the data before delving into statistical analysis in the subsequent stages of our study. Additionally, in step 5, making a decision, we will assess the statistical significance. If the p-value is less than the chosen significance level, alpha, we will reject the null hypothesis and conclude that the treatment has a significant effect. This step is crucial in drawing meaningful conclusions from our hypothesis test. In this section, we delve into statistical modeling and the significance of p-values. First, let's focus on understanding p-values in the context of modeling. P-values are instrumental in significance testing, helping assess the importance of variables and model parameters. They also play a crucial role in influencing decisions about which variables to include in the model, providing insights into their impact. Moving on, we introduce the concept of linear regression. Linear regression serves as a powerful modeling technique, particularly for unraveling relationships between variables. It allows us to model these relationships and understand their implications. Furthermore, linear regression possesses predictive power, enabling us to make predictions based on the linear relationship between dependent and independent variables. This foundational understanding of p-values and linear regression sets the stage for more advanced modeling and hypothesis testing in statistical analysis. In linear regression, the p-values associated with coefficients are pivotal indicators of their statistical significance. This statistical significance, as revealed by the p-values, helps us interpret the impact of each variable in the model. Specifically, a low p-value, 0.05, suggests that the corresponding variable has a significant and meaningful impact on the dependent variable. Now, let's visualize this concept using a linear regression model with a scatter plot. This scatter plot illustrates the linear relationship between variables, helping us better understand the modeling concepts discussed, as we can now visualize the linear relationship. Linear modeling is a statistical method that allows us to model the relationship between a dependent variable and one or more independent variables. The primary objective here is to understand and quantify the impact of these independent variables on our dependent variable. Moving on, let's explore the crucial role of p-values in assessing significance within linear modeling. Within linear regression, coefficients play a vital role as they represent the strength and direction of the relationship between variables. But how do we determine if these coefficients are significant? Enter p-values. These values assess the statistical significance of the coefficients. In other words, they help us understand if the observed relationship is likely due to a real impact or just a chance occurrence. Interpreting p-values is key. A low p-value suggests that the corresponding coefficient is likely not zero, indicating a significant impact on the dependent variable. This insight is crucial as it guides us in making informed decisions based on the statistical significance of our model. Let's now delve into the mechanics of simple linear regression, a fundamental concept within linear modeling. At its core, simple linear regression is represented by the formula. Let's visualize this concept with a simple linear regression plot using R. In this example, we've generated a data set where y is approximately twice the value of x with some random noise. Here, you can see the blue line represents our linear regression model, capturing the relationship between our xn and our yx. Understanding the simple linear regression formula is foundational as it forms the basis for more complex modeling techniques. As we move forward, we'll explore additional nuances and applications within linear modeling. Here is a quick introduction to the diverse realm of regression models. Each model has its unique strengths and applications. Let's explore. Logistic regression is a powerhouse for predicting binary and categorical outcomes. Its strength lies in estimating probabilities, making it ideal for scenarios where you need to understand the likelihood of an event occurring. When relationships between variables aren't strictly linear, polynomial regression steps in. This model is designed to handle non-linear patterns, offering a more flexible approach to capturing complex data relationships. Multiple regression takes things a step further by incorporating multiple independent variables. This model is your go-to when dealing with scenarios where there are multiple predictors influencing the dependent variable. It's all about capturing the complexity of real-world situations. Addressing issues like multicollinearity and overfitting, ridge and lasso. Regression bring regularization into the mix. These models include penalty terms to prevent overemphasis on certain variables, promoting more stable and reliable results. Each of these regression models is a tool in your analytical toolkit. Knowing when to leverage each one can significantly impact the accuracy and robustness of your analyses. We're unraveling the critical role that p-values play in the process of selecting models. Let's delve into why they're the unsung heroes of model building. P-values serve as guiding lights when it comes to deciding which variables make the cut in our model and which ones are left out. They act as gatekeepers, helping us make informed decisions about the inclusion or exclusion of variables. One of the key tasks in model building is interpreting the significance of predictors. Low p-values are our signals here. When a predictor has a low p-value, it suggests that it is a significant contributor to our model, adding valuable insights into the relationship with the dependent variable. Model building is a balancing act between achieving simplicity and retaining predictive power. P-values aid in striking this balance. By selecting variables with low p-values, we aim for a model that is not only interpretable but also predictive. Here, you see a visualization of a regression model using the MT-CARS dataset. We're exploring the relationship between miles per gallon, MPG, and horsepower, HP, colored by treatment. As we proceed in our exploration of model selection, remember that p-values are your allies in crafting models that are both insightful and effective. Here, we're delving into the pivotal role that p-values play in the construction of robust statistical models. Let's explore how these values guide variable selection and contribute to the overall strength of our models. At the heart of model construction lies the critical task of variable selection. P-values step in as our reliable compass in this process. They aid in determining the significance of individual variables within our model. When we talk about statistical significance, low p-values become our indicators. A low p-value suggests that a variable is likely contributing significantly to the model, offering valuable insights into the relationships we're exploring. Understanding p-values is not just a technical requirement. It's a cornerstone for constructing models that truly capture the underlying relationships in our data. This understanding is crucial for building models that are not just statistically sound, but also capable of making accurate predictions. Additionally, the significance of p-values extends to preventing overfitting. By comprehending these values, we can avoid the inclusion of irrelevant variables that might otherwise lead our model astray into overfitting territory. Let's dive deeper into the strategies that empower us in the intricate process of model building. Choosing the right variables can make or break a model, and here are some strategic approaches. Forward selection. Imagine starting with an empty model and gradually introducing variables based on their p-values. It's a step-by-step approach, letting statistical significance guide each inclusion. Backward elimination. On the flip side, we begin with a model that includes all variables and then iteratively remove the least significant ones. It's a methodical process of elimination. Stepwise regression. Combining the best of both worlds. Stepwise regression incorporates elements of forward selection and backward elimination. It adjusts variables at each step, providing a comprehensive strategy. Now let's see these strategies in action with an example from a fuel efficiency enhancement study. Here we've formulated hypotheses, chosen a significance level, A, collected data, and analyzed it using a linear model. The p-values extracted from this model guide our decision-making. In a real-world scenario, statistical tests would follow, and if a p-value is less than our significance level, we would reject the null hypothesis. In this visualization, each bar represents the p-value associated with a variable. As we progress through our model-building journey, keep these strategies in mind. They are the compass guiding us through the maze of variables, ensuring our models are not only statistically sound, but also insightful and predictive. As we conclude our exploration into the significance of p-values in modeling, let's recap the key takeaways that underline the importance of these values in statistical analyses. P-values are our gatekeepers in the modeling process, assessing the significance of variables within statistical models. Their role extends beyond a mere statistical test. Understanding p-values contributes to building models that are not only statistically sound, but also robust and meaningful. Drawing a parallel between hypothesis testing and statistical modeling, we find a common foundation. Both endeavors aim to unravel relationships within data. P-values play a pivotal role in this journey. In hypothesis testing, they guide decision-making, while in modeling, They are instrumental in assessing the significance of variables. Scientific inquiry relies on standardized approaches, and p-values provide just that in testing hypotheses and constructing models across diverse fields. The pursuit of continuous improvement is key. Regularly refining and validating models ensure their relevance and reliability over time. As we wrap up our session, remember that the journey in statistical modeling is dynamic and ever-evolving. Our understanding deepens with each analysis, each model built, and each hypothesis tested. Thank you for joining us on this exploration.